Welcome to MEI Modelling with Algorithms. We're on the topic of Linear Programming 1, Introduction, and this is video 1.4, Graphical Solution, where we need to find integer solutions. So we're just going to begin with a reminder of what we've done so far. So we've looked at graphical solutions to linear programming problems, which start with an algebraic formulation of the constraints, which we can plot on a graph. And we've seen two methods then for finding the optimal solution. There's the vertex method, where we look at where the lines cross and find the vertices of the feasible region and see which one's the best. And we've also seen the objective line method, where we vary this objective line until it just leaves the feasible region, and the vertex at which that happens again will be the optimal solution. But what we've been assuming all the time is that the variables x and y can take any values within those constraints, so they're not restricted, for example, to whole numbers. Now, of course, sometimes it turns out that the solution, and often this is the case, that the solution happens to be a pair of whole numbers anyway, but actually often that's not the case, even if we're in a situation where the practicalities of the situation mean that obviously we could only have integers as our solutions. So that's what we're going to be talking about in this video. Obviously there's all sorts of practical situations where the things that the variables are representing are numbers of particular items which are indivisible. So it might be, numbers of beds, numbers of ice creams, whatever it is. Okay, anything that can't be divided into fractions will require us to have an integer solution. Now, in terms of rigorous algorithms that would find integer solutions, that would actually be a lot more difficult to do, and we're not going to be looking at that in this course. So all we're going to do is we're going to use our algorithms to find the optimal solutions just as before, which may mean that gives us non-integers. Having got that, we will look nearby for any possible integer solutions. So we're not absolutely guaranteed that will give us the best one, but almost always it will do. What we're really saying here, of course, is that our feasible region is no longer a continuous region of space. It's just a set of points with integer coordinates. So really, our feasible region is a bunch of dots rather than a continuous region of the plane. So here's a simpler example of what this might look like. So we've got our original feasible region here, which is what we would get if we hadn't restricted ourselves to integer solutions, and that would have given us a solution corresponding to this point around about here. And in this case, again, because we're not really doing rigorous algorithms for this this video, this point here, 2, 5, we can clearly see from our graph that that must be the nearest solution, unless the objective line is really close in gradient to one of those two lines, which is why it's not absolutely guaranteed, but almost certainly that will be the best solution. Just on that point, I think it's very unlikely in an exam that they would give you a question in which the objective line was such that that point was in any doubt, but it's probably worth saying, just if you're ever doing this in real life in the future, that you should be very careful about that. You shouldn't really assume that that is definitely the right solution. Now, of course, maybe in a larger scale problem, one that's been less contrived to make the numbers easy, this might be more like what you see. So we don't really know exactly, certainly from the graph, we don't know exactly where these vertices are even. Obviously we can find their exact points by solving the simultaneous equations associated with the lines, and probably more often than not then we're going to find that these are non-integer values. But even when we know what those non-integer values are, it's going to be very tricky on this sort of scale to see where the integer solutions are that we're actually after. So what might we actually do in practice here? So supposing we find that the optimal solution is at point B, before we get into integer solutions. If we work out where point B is by solving our simultaneous equations, we'll find that it is at this point here, 1000 over 11 and 1500 over 11. It'll be easier in a moment to think about what these things are in decimal form. But what we're going to be doing is looking at the 4 integer points which surround point B. So point B is represented by this pair of coordinates. So as I say, it might be worth working out what these are in decimal form before we go any further. So we can see here now, if we express B using decimals rounded to the nearest one decimal place, that these 4 coordinates that we've got surrounding this are the ones which surround that point on the grid. So obviously 90.9 would round up to 91 or round down to 90 and so on. So our assumption is going to be, at least in this video, that the optimal solution must be at one of these points. The things we need to consider then is, firstly, for each of these points, is it actually within the feasible region? Because it's possible that by stepping along a bit we may have left the feasible region. And then, is it, of the ones which are in the feasible region, which one has got the highest value of the objective function, assuming that it's a maximization problem. So in this case, these 2 integer points, the 91,137 and 90,137, they actually breach these inequalities that are associated with the constraints by giving a number here which is greater than 1000, or a number here which is greater than 501. So that rules out these 2 at the top here. But these 2 are valid solutions in the sense that they are lying within the feasible region. We don't have the objective function in this demonstration, but if whatever objective function we have, we would then substitute these values of x and y into that objective function and see which of these 2 points has the highest value. So just a summary then of what we do if we know we're looking for integer solutions. First thing is that we consider the rectangle of 4 integer solutions that surround the optimum solution. You might want to think for a moment as to why we're referring to that as a rectangle, because you could be forgiven for claiming that it's a square. The 2 problems with that is that, well, firstly, on your graph you may be using different scales, so it may not even look like a square on your graph. But even if you use the same scale in the sense of the numbers themselves, it's possible that the units might be different anyway, which means that it would be completely meaningless to refer to it as a square. However, it may well look like a square on your graph. So once you've established what those square or rectangular points are, you must check all 4 of them firstly to see that they lie within the feasible region. Any that don't, you can discard straight away. Then for those that do lie within the feasible region, you have to calculate the value of the objective function and choose one which gives you the optimum value. And one final thing to look out for, unlikely to happen in an exam question, but it's worth being aware that firstly, if we have a situation where the objective line is very close in gradient to one of the constraints, then it is possible that we could find that there are integer solutions that are not on that square, rectangle I should say, that are actually the optimal point. And also, one thing to be careful about as well is if you have a point which lies on the boundary of the feasible region, then you'll have to look carefully at the inequality to see whether it's a strict inequality or one which is less than or equal to or greater than equal to. So we're going to finish now with a summary question which I'd advise you to try yourself before seeing the answer. So this is the problem that we have, linear programming problem, where you can see that we've got a feasible region which has been given to us. We're told what the vertices are, and we're told that the objective function is x plus 3y. So the question then is, which of these is the optimal vertex if we're trying to maximize p, and what is the maximum value of p? And then after that, if we are now restricted so that x and y must be integers, what then is the optimal point, and what then is the corresponding value of p? And to help you, we can see that there's an objective line here. So if you want to pause the video now, you could try that yourself. Okay, so what you should find then is that by moving the objective line up, we can see that if it went much further, we'd be left just with point B, would be the last point to disappear from that side of the line. So that means that point B is the optimal vertex, and that if we work out, if we put those coordinates 1.5 and 3, put them into here, you should find that you get a value of 10.5. But this is the question which really is being addressed in this video, which is if x and y are integers, can we then find the optimal point and the corresponding value of p? So the first thing that we're going to need to do is to think about where there are integer points near to b. So if we look at the scale here, we can see where the integers lie. If I was to try to go for something like 1, 3 there, well, I can already see that that's outside the feasible region, so I'm not even going to bother drawing it. The ones which are possibilities are going to be 1, 2, 2, 2, and maybe at a stretch 3, 2. But there are no others that could realistically be the optimal solution when we need integers. So let's now try these 3 points and see what the value of the objective function is at each of them. So at 1, 2, we can work out the value of p. It's going to be, well, we can see p is x plus 3y, so it would be 1 plus 3 times 2, which of course is 7. And then if we do the same thing for the other 2 points, we'll get this. So we have values of 8 at 0.22 and 9 at 3.2. So clearly this point here, 3.2, is the optimal point, and that has a value of objective function of 9. And of course that is less than the value of 10.5, which would have had if we weren't restricted to integers. So that concludes video 1.4, graphical solutions, where we're restricted to integers. The next video will be 1.5, visualizing 3D